Hello everyone. Today we'll be talking about designing PV strings for the Midnight Power all-in-one inverter. This is essentially the same method that you'd use to design the PV strings for any string inverter or charge controller. But if you've been working with microinverters a lot, you may not have seen this. So we're going to go through what the different relevant parameters are and how to decide on how you're stringing your PV modules. First, we're going to look at the spec sheet for the inverter, and scroll down to the second page here, and here's the important part right here where we've got maximum PV input power, maximum PV input voltage, startup voltage, MPPT operating voltage range, maximum usable PV current, and max current per MPPT. A little bit about what each of those means. 15,000 watts maximum PV input power. That's the maximum that the combination of all three MPPT inputs can handle. If you have any more power than that, it's just going to get clipped at that level and you won't get that power from the array. It won't hurt the array, or it won't hurt the inverter, as long as it doesn't exceed some of these other parameters farther down. There's several of those which can hurt the inverter. In addition to 15,000 watts maximum for the combination of all the MPPTs, we also need to think about 8,000 watts maximum for each MPPT input, and also we can only do 11.4 kilowatts maximum AC output. So if we've got 15,000 watts coming in, we can have some charging the battery at the same time that some's being converted to AC power, but we can't convert all of that 15,000 to AC power. Next one here, maximum PV input voltage, 600 volts. This is one we absolutely have to adhere to. If we exceed 600 volts, that can destroy the inverter. And this is open circuit voltage of the PV array on the record cold day for that location. So the colder that PV modules are, the higher a voltage they put out. So on that record cold day, as soon as the sun comes up and hits the PV array and it hasn't warmed up from overnight record cold temperatures, that's going to be our maximum voltage. So we need to look at that voltage, not just the rated voltage of the PV array. When we go through the string sizer, you'll see that it automatically calculates that correction factor based on the temperature. We've got startup voltage. We need at least 90 volts to start the MPPTs. And then once they're started, they can operate anywhere between 70 volts and 550 volts. Now, they will operate down to 70 volts, but I prefer to keep them above about 150 volts minimum, just because the efficiency falls off quite a bit once you get below 140, 130 volts input. So while it will operate down to 70 volts, it's really not ideal. So I try to shoot for 150 minimum. This is the maximum usable current that each of the three MPPTs can handle. 30 amps on number one and 22 amps on the other two. It will clip any higher current than that. But what we need to look at a little closer is the maximum current per the MPPT. And this is actually defined in the NEC electrical code. Maximum current is defined as 1.25 times the rated ISC, short circuit current, of the panel. So that cannot exceed 40 amps or 30 amps for the MPPT 2 and 3. When we're thinking about that, we also need to consider what's our contribution from bifacial panels. So if our rated ISC is, say, 10 amps, but we're getting another 20% from it being a bifacial panel, we need to add that in there as well. And that's also something that the spreadsheet does. So those are kind of our critical specs off of the inverter that we need to keep track of. If we exceed 600 volts, we can damage the inverter. If we exceed 40 amps or 30 amps or 30 amps on the other two MPPTs, maximum current, we can damage the inverter. If we drop below 70 volts, it just won't work. There's no damage. It just isn't harvesting solar energy. And if we go above 15 kilowatts maximum, we're just clipping power. Going back to our spreadsheet, here we are. So we've got a bunch of information we need to enter for our location, starting with the specifications for the PV modules. Here we've got a Mission Solar 435 watt PV module, and we need to enter the rated power, VMP, that's volts at maximum power, at STC. STC stands for standard test conditions. This is not what we see in the real world usually, but it's a standard set of conditions that we can test all the modules at to give a standard rating and compare modules. But we need to basically change those values based on our conditions to see what it's going to be doing in our situation versus STC conditions. But the spreadsheet does that all automatically when we put in the values. So what we'll look up is standard test condition values off the spec sheet. VMP, VOC is open circuit voltage. IMP is our rated current at STC conditions, and ISC is our short circuit current. We'll also need to think about, are these bifacial modules? And if so, how much reflection are we getting? Are we expecting another 10% if it's just getting a little bit, or might we be getting 20% if we're a really ideal situation, snow-covered field underneath a pole mount, for example? And then these two are critical. TK-VOC, that's a measure of how much does our VOC change with changes in temperature of the solar panel. And TK-VMP, sometimes this is also called TK-PMP. How much does our maximum power voltage change with changes in temperature of the module? We're going to look at the spec sheet and see where we get those from now. Here's the spec sheet for this module. See, this is a standard kind of high efficiency 108 cell, half cut cell module. This one's made in Texas, I believe. And looking at our electrical specifications here, you can see we've got a couple different modules on this sheet. So we're looking at the 435 watt version. So we're going to look at this, and we've got our maximum power output. That's one of the things we need. Here's our short circuit current, ISC, open circuit voltage, VOC, rated current, IMP, and rated voltage, VMP. So those are five of the values that we need for our spreadsheet. Here's our temperature coefficients. You can see here they've actually just written it out rather than using the abbreviation. Temperature coefficient of VOC, negative 0.25% per degree C. Temperature coefficient of Pmax, sometimes this will be of Vmax. They're the same numerical value, 0.29% per degree C. And notice that these are negative numbers. That's because the colder that you put the panel, the higher your voltage goes. The temperature coefficient of short circuit current here is a much lower number. You'll see it's got a whole extra zero here, a whole order of magnitude less. So it really doesn't change all that much. So we generally ignore that. But the temperature coefficients of VOC and Vmax or Pmax are the two that are really critical to this design. So that's what we're going to take over to our spreadsheet now. See, we've entered those in there. One note, this is showing degree Kelvin. A size of a Kelvin degree and a Celsius degree are the same, so you'll see both of those listed on different spec sheets sometimes. Now we need to know, what are our climate conditions for the site? How cold and how hot does this site get? Here we put in -25 Fahrenheit and 84 Fahrenheit. Now this is the record low temperature, but for the hottest one, we just do the average high temperature. And that's because that doesn't destroy the inverter if we exceed it. It just doesn't perform as well. This one we use the record low temperature because we really want to make sure we never get a higher voltage than what we'll see at that temperature. And the spreadsheet automatically converts those into degrees Celsius right here. We also need to specify the mounting adder. And what that is for that high temperature, the average high temperature we said is 84 degrees Fahrenheit during the hottest month. But those solar panels are sitting in the sun. They're going to be a lot hotter than that temperature of the ambient air. And how much hotter depends on exactly how they're mounted, how much air circulation they're getting. These are just kind of ballpark numbers to put in there, but typically on a pole mount, we might see 20 degrees C higher. In a really windy location, it might be less than that. A ground mount or a tilt up on the roof where there's still quite a bit of air circulation, but not quite as much as a pole mount, 25 C. If we're a real nice steep roof where we get some good chimney effect from that hot air rising up and kind of pulling itself out from under the array, we might see 30 C. And if it's a shallower roof, really not much air circulation at all, we can see 35 C or even more temperature rise over ambient temperature for the temperature of our actual PV cells. So we put that in this cell right here, and the spreadsheet calculates our maximum operating temperature of the array, in this case 147 Fahrenheit. I've actually measured arrays easily in the 180 Fahrenheit range on really hot summer days that really don't have good air circulation. So they can get very hot. Here, the spreadsheet does the work of all the math and with the inputs that we've selected, and it's come up with our VOC is going to be 14% higher than the STC value at that record low temperature, and our VMP is going to be only 88% of the STC value at that hot temperature. So on that cold day, we're seeing a lot more voltage out of our array, and we need to make sure we don't fry the inverter. On a really warm day, we're seeing less voltage out of the array, and we want to make sure we still have enough voltage to be the minimum that the MPPT input wants. Spreadsheet also calculates our minimum modules in series and our maximum modules in series. And for this minimum, it includes a 25% safety factor, because even though we said this doesn't harm anything if it goes below that, it does stop collecting energy from the PV array. And over time, we expect the module voltage to decrease as we have degradation of the PV cells and also possibly higher temperatures than our current average temperatures. So you don't have to put that safety factor in there, but it's a good idea to always have that. Just because I've had situations where when a brand new array was installed, it worked pretty good, and then 10 years later, those modules just weren't putting out as much voltage as they were when they were new, and it started browning out on hot summer afternoons and not being able to function. So having that safety factor in there is important for that, because we know it's going to degrade over time. For the maximum, we never want to exceed that, but over time, we're probably not going to be getting colder record low temperatures. If we think maybe we will, we might want to put a lower value in there for that. Another thing this calculates is for the amperage, how many strings can we put in parallel on the different MPPTs? In this case, it says we can put 2 strings on parallel on the first MPPT, but only a single string on MPPT 2 and 3. Now, here we can enter the number of modules in series and the number of strings in parallel on each MPPT, and it will kind of show us the totals for each one. If we put in our maximum, which we said was 13 here, it calculates, and any cell that turns red like this is saying there's something wrong. You're exceeding an allowable value. You need to change the design. In this case, we're over 8,000 watts on one MPPT, so it's not going to be able to handle that, and it's going to be clipping. Our rated VMP is 433 volts, but here's the interesting ones, and these are the ones with all those temperature corrections applied. At that record low temperature, we're at 587 volts, getting pretty close to 600 volts. We can't do one more module in series if we tried. Now we're up to 632 volts. That's going to cause failure of the inverter. All of the FETs in the MPPT section will eventually fail, and that's a pretty catastrophic failure of the inverter there. So we never want to exceed that. So let's go back to 13. And amperage-wise, we're okay. 26.14 amps for our rated current, and our I max, which remember that's 1.25 times the ISC as defined by the electrical code, 34.5 amps, still less than the 40 amp maximum that the inverter can take. So our problem is we just have too many watts on that channel, and it's going to be clipping. So let's take this back to 1 string, even though we could get away with 2 strings. We'll do 1 string. Now looking at this one, we're looking at our minimum modules in series, which was 3. And if we take a look at this, we're at 89 volts here for our VMP at high temperature. That's over the 70 volt minimum. The inverter will function, but it's not going to function great unless we keep that above about 150 volts. So maybe we want to put 4, we're at 118 volts, 5, 148. So effectively, 5 modules in series is really what we want to shoot for as our minimum here. Even though it will still function with 3, it's just not a very good design. It's not going to be as efficient. Now here we've got 2 strings in parallel, and it's telling us your amperage is too high. Our rated IMP is 26.14 amps. It's going to start clipping at 22 amps, so we're going to be losing power there. Plus, we're at 34.5 amps for our I max. If we go over 30 amps, we have a potential of actually damaging that MPPT input. And again, that could be a catastrophic failure, just like an over voltage input. So we cannot put 2 strings in parallel on the MPPT 2 and 3 of these particular modules. But we could do a full string of 13 on them. So you can play around with these numbers and see different options that work. Maybe you've got a roof plane that has 14 modules. Well, 14 modules were too high a voltage. But what if we did 7 and did 2 strings of that coming into MPPT 1? That's an acceptable design with all the different parameters. So the spreadsheet here gives you the option of, once you've got your module parameters entered, you can quickly kind of look at different options for longer strings, parallel strings, shorter strings, what's going to work for your particular situation. This spreadsheet is available on our shared drive, which if you're on our installer training email, you've already seen that shared drive. If not, you can email us and we can get you signed up for the training emails and get you access to that shared drive and this spreadsheet to let you do these calculations and see what kind of string combinations work with our inverter. Thanks.